morning. Thank you very much for waking up early and being here so promptly. So 4 years ago, we got invited to this fantastic project that IPCC, Fujitsu, and Intel were putting together. And I'm very happy to have participated. The project finished last month. It was a 4-year project. And it led us to see, to have a peek into the future of how can we address I/O issues generically at the exascale, but in particularly for my interests, how can that help us achieve exascale weather forecasting systems? So, and that's what I will show you today. But to start with, I'll start by explaining you what is really the challenge here, because it's slightly different than your normal, what you usually perceive as standard HPC simulations, because there's a time-critical issue into it. So, first of all, who is ECMWF? This very strange acronym. We are the European Centre for Medium-Range Weather Forecasting. And what do we do? So we are a member state organization, international organization, countries all over Europe, not directly linked with the European Union. So we have member states like Turkey, who is not part of the European Union. And what we do, every day, we run 4 times a day global weather forecasts at a very, very high resolution. And those forecasts produce this global prediction of weather, for which we still do and prepare products for all our users. And then occasionally we also run extended weather forecasts to monthly, and we also do some seasonal forecasting. And aside from that, our HPC is also used to run the research to feed in that weather forecast. So we have a time-critical part of our workloads and a more like non-time critical part showing here is the new data center that is currently being built. We will soon move our data center to Bologna. And there we will still have a pre-exascale machine, but eventually, with time, we will arrive to exascale, as we all will, and we have to solve our I/O problems for that. So let me show you first a very, very simplistic view of what we do, so that you can understand. So we ingest global weather observations. That goes to a system that we call acquisition. That is fed into the IFS model, which is our weather forecasting model. So we compute the initial conditions. Using those weather global observations, we reconstruct the initial state of the atmosphere from where we start the simulation. We step forward in time, and we produce some fields, which is a kind of like raw output. From that raw output, that's not enough, because the users are not interested in everything. They may be interested in kind of like post-processed, user-specific products. And so the product generation kicks in, and while the model is running, we are already reading and preparing the products for our users. And once the products are ready, we pass them to a system called product dissemination that ensures that a certain weather forecast is delivered at the same time everywhere in the world. Because we have to provide a fair playing field. We cannot allow, for example, an energy client if he would get the weather forecast earlier, he could play the market against other clients. So we have to ensure, we have a system dedicated to ensure that everything arrives at the same time to everybody. Right. To look at the I/O issue, I'm going to zoom in into one part of that problem. And that is where the model is running the forecast and outputting the fields, the raw data. And it outputs today, you can guess, to the parallel file system. Happens to be Lustre, but a parallel file system. At the very same time, minutes after a certain piece of data is written, the product generation is already reading it and processing it. Okay? And once the products are done, guess where they're going to be put? They're going to be put again in the parallel file system. And once they are ready to be pushed to the dissemination system, they are ready, and dissemination pushes them out. On the side, we also have the mission to provide a perpetual archive for all the forecasts and all of the observations forever. Okay? So we can go back and given certain observations, we can reforecast the past. And that's very useful, for example, when you need to recalibrate models. Okay? That time window is what's important. It's where the current I/O issues that we feel is or are. The fields that we write, 70% of the data that we write is read within minutes. Okay, and that's today. It's about we write about 20 terabytes within a short window of an hour, and within that short window, we are going to read 70% of those 20 terabytes. Okay? That creates a problem. And this can illustrate it with a simple experiment. This is not numbers from our operational forecast. This is a run at a 9 kilometer 50 Ensemble member. We cannot do that today with our supercomputer. It's too heavy. But if you run the model, you will see that the runtime, if I run the model without I/O, is 5,700 seconds, okay? On 2,400 nodes of our system. If I turn on I/O, I add some more nodes for to handle the I/O. We have an I/O server architecture. And with more nodes, we actually go slower by 17%, just because we are writing. And if I turn on the product generation, which is the one that reads at the same time, I give it more nodes because you have to compute that, and we go slower by 26%. So just because you are reading the data, so totally decoupled, these are not coupled parallel MPI jobs, okay? They are not coupled. They are independent MPI jobs in different sections of the supercomputer, only getting coupled via the file system, all right? So this is completely I/O related. This is completely choke point on I/O, right? And the reason is that the parallel file system is today a workhorse for us, okay? We get acquisition of observations, guess where it goes? Parallel file system. We produce things, goes to the parallel file system. We do product generation, we go to the file system. We disseminate, and the archive, everything somehow involves that parallel file system. Even if it's not using a node of the supercomputer, we have servers and services that run and use the data in that parallel file system. So data is central, and everybody knows that, right? It's becoming like a resource. Data is a resource. You want to get your hands on data. Data is becoming the commodity of the 21st century. And solving I/O is going to solve and allow us to do more with that data. And we have an issue with data growth because we grow our data sizes about 40% yearly compound rate. So every year, more or less on average, every year the data sets grow by 40%. And you can see that on this exponential curve. This is just the products that we send to users. We send per day more or less 30 terabytes per day across the world, okay? And this is a growing exponential curve. And this is the projection of how the volume output just for the Ensemble is going to grow in the next 6 years. So, where does that growth come from? It comes from resolution. For example, here, you can see that today's forecast is that line over there. In memory, one single field is a slice of the atmosphere, horizontal slice of the atmosphere. In memory, expanded, not compressed, is 50 megabytes, right? We have 137 levels of the atmosphere at the resolution of 9 kilometers. And we plan to arrive here, right? We want to arrive here. We want to do 1 kilometer resolution across the world, maybe 200, 180 levels. But one single slice of that atmosphere will be 2 gigabytes in memory. And we have millions of them, okay? So this is where the real challenge is. Because we want to do this. We want to do a 1 kilometer simulation. This we can do today. The computational problem, the science is ready, okay? We can do this today. 1.25 kilometer resolution across the world. What can you gain with that? Look, we turn off cloud parameterization. Today, clouds, the way we put clouds in the model is a parameterization. It's kind of like a model, it's complex physics, but it's not the true physics. We are not letting the Navier-Stokes equations with moisture create the clouds because there are scales missing, okay? But at this level, you have already the correct convective scale. So you can let the model now create the clouds, and this is what you see here. But it's not only that, it's not only resolution. In truth, there are 3 axes that bring you the quality of a forecast. One is the accuracy you get by the model resolution. To know your reliability of a forecast, you run an ensemble, you run 50 members, and here you have the other axis. The more members you add, the more you can explore your space, and therefore you can have higher reliability knowing that indeed this forecast is the most likely. But there's always another axis that people tend to forget, which is model complexity. We have more or less 1/3 growth in each of the axes, okay? So 1/3 is actually from more science, right? You can, for example, think somebody improved the way the land surface is discretized. It will add new fields for the output, okay? It used to be land was just like one single layer. Today, we are looking at multiple layers inside of the Earth. Why? Because we are building truly to have a proper weather forecast, to compute how, for example, snow melts correctly. You need to have more complex physics, and you need to walk towards a true Earth system model where everything is coupled. Ocean, waves, sea ice, and all that is bringing the extra growth. And it's not only that. We have extra growth coming from observations because more satellites are going up. We want to do higher accuracy and time. And all across our workflow, we want more data, right? This is, in my team, this is what we do. We are developing the technology that will allow the scientists to do that, right? But we have to solve this I/O problem. So how does it look, a problem of storage and I/O at the exascale? I'm going to call upon here one of my favorite computational methods, right? And it's not using a supercomputer. It's using the old back-of-the-envelope calculator, right? So let's have a look of how large is a 1 kilometer 50 ensemble member weather forecast. And if you have seen my presentations before, the numbers are going to be slightly different because I cranked it up a little bit. So I made it very clear that this is 50 members at 1 kilometer, okay? So if you start with 50 members compressed, we already did compression, so no gain there. We have today at 18 kilometer ensemble, you have 20 terabytes is what that takes. If you crank up the resolution once to 9 kilometers, it turns out that it's not a 4 times increase, although it should be, but the Earth is not a square, although many mathematicians like to model it like that. The Earth is a sphere, right? So we kind of save points at the poles. That's why it's 3.3, not really 4. We crank it up again. We increase the levels to 200, and we increase it again for 2.5 and again for 1. So these are all increases of volumes, right? And we end up that we need 3.6 petabytes to have a 1 kilometer 50 ensemble weather forecast. And I think by now we passed the exascale. I think it's not the exabyte that really matters, right? It's the exascale to compute it. But you need this is, I think, is going to be the data set that we will have to work with. So, and this is where Next-Gen I/O comes in, right? Next-Gen I/O project, so 8 partners, IPCC was the leader. We were brought in to do 3 things. One, to help out with the requirements, setting the requirements. This is a co-design project, very successful in my opinion. Really very good interaction between the application people, the hardware people, the middleware people. And then they designed, Fujitsu together with Intel created this HPC node with 3D cross-point in it. We'll see what is that later. And then with this technology, we had the aim to demonstrate how can that help for a weather forecasting model, and particularly how could we use it together with our I/O server inside IFS. So what's that technology? What is special here? It's NVRAM Intel Optane DCP-MM. So this product is based on a technology that provides a density similar to NAND flash memory, but it has better durability and has better speed and latency. And it's non-volatile. So, but for me, the key point really is it's a very, very high density storage medium with very low latency close to the compute. Very, very close to the compute, right? So this, how do can we use? We were planning to use this. We could use this like large burst buffers, right? That's the obvious. It's close. Let's put the data there and slowly trickle in the background. But if you think it's on a time-critical workflow, where the checkpoints are not really where the I/O gives us troubles. It's the real output data that is the trouble. Is that we think that we can use this as a staging mechanism for the product generation to get its data from. So it's really like a storage system, right? And how did we think about it? We took our I/O server technology, which basically takes the data from all the compute nodes, funnels them through an MPI aggregation to the I/O nodes. Those I/O nodes do the compression, the encoding, and do the I/O. And today, those nodes, they place the data in the persistent storage, in Lustre. And we thought, OK, let's just simply substitute that with NVRAM. But how do you do that? Because you still need to do the rest. You still need to do put the data for the archive, for the other users of the data. It's not only the time-critical window. So we thought that, OK, let's put the data in NVRAM, and we have some kind of library, we call it MultiIO, that does the kind of the multiplexing. It sends the data to the product generation, but at the same time, and that will be in the time-critical window, but at the same time, we can send the data to other destinations, including cloud. We will come back to that at the end of the presentation. So we implemented that, but it still doesn't solve it. How do you put all the data in NVRAM? And it's a bit harder than you think, because for NVRAM you have to prepare the data, but then you have to find the data. You know, imagine a 20 terabyte data set, but a consumer of the data only wants a piece. Where does he go? So I'm not going to scan all the data. I need to find it fast. It's a time-critical window after all, right? So we piggybacked on the fact that we already had a layer in our system called FTB, and in that layer we have basically an object store. And we decided, okay, what you really need for this system in Extern I/O, because you have 30 nodes with NVRAM, you somehow want to see this as a whole, right? So on top of what we already had, we redesigned our software stack, I/O software stack, and we said, let's come up with a distributed object store, right? Its advantages that's transactional, no synchronization, all the nice things that an object store brings. It's domain specific because it's targeted at the weather and climate, and it works like a key value store, right? And the advantage is that brings and creates an abstraction where in the background, I can now have different storage policies. And one of them will still work with Lustre, because that's the technology we have today. But we can prepare for, say, NVMe. We have been playing a bit with NVMe and with NVRAM. And you did use these different libraries to access both. And it provides things like range queries. You can say, give me all the fields, give me just these ones. So, but why really do a domain-specific register? What are we gaining with that? Well, flexibility is first. I think we are in a period where many things are changing in our market, in HPC, in I/O certainly. And I would like to have the flexibility to not bind myself to one and allow the technologies to evolve and be ready to change. So that is what this brings. It creates me an abstraction that hides away the technology, and I can adapt to it. And at the same time, I can support existing systems that are tied to POSIX. It also provides me consistency. It's a way of the accessing the data consistently across all applications. So the model will write the data in a way that describes the data, and the product generation uses that data in the same way. And it's the same way I go and get it from the archive. So we have accessed the data through semantically meaningful metadata, okay? And I'll go into that, what that means. We are piggybacking on the fact that for 40 years, well, 30, 40 years, ECMWF has had this Mars language that describes all the data at ECMWF. Every single byte that we have produced can be accessed with this language, all the way down to forecasts done in 1987, okay? And you describe this, it's a retrieve me the data. There are some parameters that the scientists have been trained to use, but they don't talk in files, right? They talk in science terms. They say, give me Z as geopotential, T, temperature, at time forecasts at 12 o'clock, level 1,000 hectopascal on the date of the 2016. So this is the forecast of that date, right? And crucially, when they run their experiments to prepare new models for the future, they access the data in exactly the same way. They just say, oh, it's instead of OD, which means operations, it's RD, it means research. So this is a research data, and that XVER there is the identifier for what particular research experiment he is running. And you note there is no name here. We don't say that the data belongs to a user. If the user wants to share data with another user, with another researcher, he just sends him this, and you can find my data in this way, right? So this abstraction has led us to a unique and semantic way to describe all our data, and also allowed us to also find the data. So that's how you find it in our fields database. So the semantics of this database is basically transactional, ACID principles, asynchronous, consistent, meaning you write, flush, and your consistency is guaranteed on the flush, okay? It's immutable, so you write once, you never delete internally, so there's no overwrites, okay? So what you gain with that is that data gets masked, and you can have versioning for free. So you can go back and say, oh, I want the previous thing. And it's operational. We brought it in operations in June this year, right? So this is actually the list of the stats of the first day we ran it in operations. You can see here the total size, nearly 100 terabytes, because it's in one day you get 4 forecasts, nearly 100 terabytes. And the size of the index, to index all this file, is 12 gigabytes. So that's less than 1% to index all the data of the data set. Okay. So for that, we designed an API. You have very simple API that people can in our center can code with without having to know what's inside. Just archive. You pass it a buffer. This is my object, and archive it with this metadata. Metadata being those keys that you just saw there. You can retrieve it with the same keys. But crucially, this is allowing us to compose. That flexibility of this API is allowing us to hide really interesting things behind. So the user will be sitting here. In this case, the user is the model, writing data. But we can do very interesting things behind. We can say things like, can do data routing. Say, oh, this is operational data. Let me send it this way. Oh, this is research data. Let me send it that way. Oh, let's distribute the data. Let's shard the data in pieces and use different locations for the data. Let's not write locally. Let's write it remotely. Let's send it over the wire. And why not having different types of storage systems? And so this composition we developed it in NVRAM and has allowed us to bring together all the nodes, all the NVRAM and all the compute nodes that we have in the system and see it as a whole. Okay? And you can see that in a certain way in this picture. We can take a subpool. So imagine we are not given the whole NVRAM prototype, we get just 4 nodes, but it allows us to create a pool of data where you access just those 4 nodes and you write just there, and that experiment just exists on that pool of data. So enough of talk of what have we done. Let's see some results. The NVRAM prototype in the end is this. It's these blades were built by Fujitsu and Intel. Each blade has 3 terabytes of NVDIMM. dual socket, 48 cores, 192 gigs of DRAM, and we have 34 of them. And how did we use this? We took, it's a simplistic view. We took, say, imagine you were given 4 nodes. You spin up a server in each one of them that is going to provide or project, if you want, access to that NVRAM. You have the producers of data, in this particular case, something that mimics our operational forecast, because there is no, in the next-gen I/O prototype, there's not enough compute power to really create terabytes and terabytes and terabytes of data from a weather forecast. We would need many thousands of nodes in today's technology. So what we created was a kind of like something that mimics the operational forecast and just writes data like crazy. And then you write and you spread the data. But you don't do it just like that. You do it like that. Everybody writes everywhere. So the same node that is serving the data and producing the data is also serving this. And it's reading from everywhere. So this is the test for which you're going to see results now. So we run that. And depending on the number of nodes and the number of write processes we get, we arrive to nearly 72 gigabytes per second. But these are not hero numbers. This is not IOR. This is true application data as seen by the weather forecasting model with flush semantics. So we are doing waits for flushing, making sure everything is on storage media permanent before continuing to the next forecast step. We do the same for reading. Reading, you get a little bit less performance. The reason is, well, you have to find that data. You have to look for where you're going where the data is really residing. And we are not cheating here. We're not streaming. We are randomly picking fields from our data set and getting it out, okay? So I think that 70 to 60 is not too bad. But the most interesting thing is that when I ran, here we ran a smaller Ensemble forecast, MultiIO, okay, against the Lustre system that we have attached to this, and we get that. So with I/O only, with product generation. So again, that slowdown that I showed before. But if I use the NVRAM, look, it's even a little bit faster. Of course, it's within the error margin. But what I'm trying to say here is that we don't see slowdown at all, okay? And if you go to these nodes and you inspect what is happening at the NVRAM level, it's twiddling its fingers and says, is this the only data you're going to send me? I can do more. Right? We inspect the queue lengths on the side of the server, and they are always around 1 or 2, because it's the fields that are in flight. Right? The bottleneck is definitely not on the NVRAM itself. So this is what we have today on an operational file system. Okay? Today we have 44 gigabytes of, on the best days we get 44 gigabytes per second. On next-gen I/O, we achieve 72. This is with 16 nodes. Our operational Lustre system takes 288, and it's a beast on the floor, right? So to me, but we're still going to use these parallel file systems. Don't get me wrong. I don't think these are done. We will still going to push forward with that technology. But to me, this is a truck, okay? You put a truck in a motorway to carry lots of things, right? But this, to me, is a racing car, okay? And we can use those for very specific things, right? And we can do things we have not thought of doing before. So let's go back to that calculation. Can we do a 125 Ensemble forecast? So 50 members compressed, that's what we need to do, 3 petabytes in 1 hour. Oh, don't forget, we also read. So let's increase that by 70%. And at that resolution is about 6 petabytes. Time to solution, 1 hour, that's what we have to do a forecast. So we need to do 1.7 terabytes per second. On next-gen I/O performance, on 16 nodes, we get 72 plus 60, 132 gigabytes per second. Required number of next-gen I/O prototypes, so what we have today in IPCC, is 213 nodes of next-gen I/O would do my exascale problem, right? That's only 7 times what we have there. And this is today. However, I'm only expected to have this in 2035. By then, the technology should probably be a bit cheaper and scalable to give me 200 nodes. So I think this technology does address Exascale. And it takes us, but I want to point out something more. Let's think of what else can we do with this technology. Is that we want access across, users want access across our 6-dimensional hypercube of data across different axes, because that's how they use the data. Each user wants time series or statistics across the ensembles. And this is allowed, is open now by the NVRAM, because NVRAM brings you byte addressability. You do not have any more to seek, wait that the disk spindles reach position and things like that. The latencies are so much lower that we will be able to deliver this. So honestly, I think we will see, I hope to see a time where these systems can sit next to the HPC. The HPC is your big producer of data. But on the side, you have things like the cloud. You have things like AI algorithms. You have things like high-performance data analytics that come to the data, hammer it in ways that today, if they would do on the parallel file system, you would slow down and grind to a halt. But today, in the future, you'll be able to do that on these very low latency systems. And I don't think it will substitute your parallel file system, but it will be there for other purposes too. Okay, so those are my messages to take home. And questions.
Thanks, Jim.